Okay, students, friends, Romans, and countrymen, lend me your ears. We're going to be talking about angular momentum. Actually, we're going to be doing some demonstrations and doing some clicker questions about angular momentum in just a few minutes. And then we're going to talk about heat, thermal energy, which will be our main topic for the rest of the week. But before we do that, I have a couple announcements relating to Exam 2, which is coming up a week from today. First of all, I have office hours tomorrow, Wednesday, 9 o'clock to 11 o'clock in the morning, in room 158, which is just off the atrium in the Physical Sciences building. In addition, Miss Caroline has office hours on Friday, 1:30 to 2:30 p.m. in the atrium of the Physical Sciences building. So, and I know she was meeting with students. Did you have students on Friday?
No, I don't.
Okay, she only had one visitor on Friday, but you know, if you can make it, if you can't make it to mine, but you can make the Caroline's, that's really going to help you get ready for the exam, because Caroline knows the ropes pretty well. Also, SI regular sessions. If you think about it, look at that schedule: 1:30 to 2:20 Thursday. That's after Thursday exam. Your exam Tuesday is going to be everything up to Thursday's exam. All right. So this Thursday SI, perfect for studying for the exam 2. Friday SI, perfect for studying for exam 2. Monday and Monday SI sessions, also perfect for studying for exam 2, because exam 2 comes on next Tuesday. So you actually have 4 regular SI sessions to get ready for exam 2, in addition to my office hours and Caroline's office. Now, just like on TV where they say, wait, there's still more, you also, I just learned this last hour from Maria, you also have SI review for the exam, a 2-hour session, Thursday night. That's this Thursday. Downstairs, classroom building 2, room 106. Okay? And Maria will post this in web courses discussions. And but go ahead and jot that down too. So excuse me, you have a lot of opportunities to get ready for exam 2. Also, another thing I want to mention before we get down to brass tacks, you're going to have a little bit later this afternoon a new web courses area that's going to be open for taking one test. It's called a diagnostic test. And you'll see it's not activated yet, but it'll activate this afternoon after lecture. And so it'll show up on your to-do list. And it's like a 10-15 minute little mini quiz type thing. And it's not part of your semester grade for this class. It's open to all physical science 1121 students in all the lecture sections and in all the online sections. And it's a way for UCF to kind of assess or take a snapshot of what the students are doing and kind of use it for planning, so that we don't use this data for grades and stuff. But it is helpful to UCF. So take that, click in there as soon as it lights up this afternoon, and take it. And it'll be open until, I think it's open until Saturday night, so you have several days to take it. It's like a 10 or 15 minute chore. It's not too hard. All right. Any questions about that, Jazz? No, you don't get a grade for it. I just was saying you get a score, but it doesn't go into your semester grade for this class. It goes to the provost's office or something like that, and then they just sit and analyze them and stuff. But they don't really, they don't really care about you as a person. They just care about this, this big herd of students, because they're gonna do averages and stuff, and so I care about every student in here. I keep track of your semester grades, but not that stuff, not this GEP stuff. So, all right. First thing I want to do with you is up front. Can you go to all on, please? We're going to do some demonstrations. I'm going to pause the. You do some clicker questions in just a minute, but before we do that, let's go over what we just saw. All right, so if you haven't taken notes, get your notes going now. Now, as I mentioned, the key to the first and the second is that we have a low friction ball bearing system. Now, when Ashley pulls the hand weights in, for which the mass M is about 2.2 kilograms, it's 5 pounds. So she brings it in to a smaller R value. And as measured from the axis, so in the middle of this diagram here, you can see a vertical black line. I don't have a picture of the student, just the lab stool. But from that axis, R is smaller. And that means that MR squared for each hand weight is smaller. Now, both hand weights are the same mass. All right? They're identical weights. So the change to the moment of inertia of Ashley is principally from the hand weights, and she's brought them in. So 2mr squared is smaller. So her total her total moment of inertia, the sum of all the mr squareds for every molecule and atom in her body relative to that axis is smaller. And for that reason, the angular velocity, lowercase omega, has to be bigger. It's got to spin up because angular momentum has to be constant. Not angular velocity, not moment of inertia, but the product of those two, I times omega. So if I get smaller, omega has to get a little bit bigger. Inversely proportional. All right? Now, the other variation, when she started with the hand weights in close and pushed them outwards, and actually, it took a little bit of work it wasn't easy to push them outward, right? Okay? It took a little bit of oomph to push them out there and to bring them in. So when she pushes the masses 2-point-something kilograms outward, she's going out to maximum R, as far as her arms will reach. So when she's in tight, the distance R from the rotation axis is maybe, I don't know, a few centimeters. But when she's out here, you're talking maybe half a meter, 50 centimeters or so on the left and 50 centimeters on the right. Because that's the case, 2mr squared is larger. You agree with me? You see it? Yo, with the hat. I just saw you nod. Is it making sense? Yeah, good. Good. And because that's the case, omega has to get smaller now. Why? Because you have to keep angular momentum constant. Now, if you don't have good ball bearings, your spin angular momentum is going to degrade. It's going to go to zero. But with this system, we got good ball bearings, and you'll just keep spinning, for a good 5-10 minutes. Come here.
What is the W again?
This kind of curvaceous W here, right here in item C, 2C and 3C, is lowercase Greek letter omega. It stands for angular velocity. Okay? So that means how many degrees per second are you spinning? Or how many radians per second are you spinning? Right? Because you don't really want to, because for a rigid object, Camille, you can't really say that the object has a certain number of meters per second, because the stuff at, Camille, out here at maximum R, these things out here where your hands are, they're really moving. But something in close, like right here, when you're in close, they're not really moving because it's a small circle. Same amount of time to go around the circle, but it's a smaller circle. So stuff in here is slower, stuff out here is faster. So you don't rate for angular motion, spinning motion, you don't use meters per second, you just use degrees per second. Okay. Angular momentum is a constant. All right? And because that is true, omega and moment of inertia, I, change. If I gets bigger, omega gets smaller. If I gets, and what this student is doing, she's changing I. All right? She's making, so when, Kane, when she has the hand weights in here tight, small I, because small R for the hand weights. When she's got the hand weights out here, big I, because big R. She's got a maximum R. All right, so that's the change. And so what she did, Ashley changed moment of inertia by bringing them in or pushing them out, and the omega changed to keep up with that. All right, another question. All right, let's keep going. Now, something I want to go over with you before we tackle the second demonstration, and that's the right-hand rule. Now, this is the right-hand rule for angular momentum and a bunch of other things, like angular velocity. Use your right hand, okay? So that's this one, all right, on the right side of your body. And curve the fingers, now, in the sense that the spinning object or the orbiting object is moving. Okay, now for us, I always spun up Caroline's bicycle wheel so that it was always moving from right to left. No, wait a minute. From left to right, this way. Okay, so now remember I use my right arm to curve like this? Okay, think of your right hand as curving like that. And then when you do that, your right thumb points in the direction of the angular velocity arrow, angular momentum arrow, and if you're actually pushing, the torque. You know, like when I was hitting that wheel tangentially, I was exerting some torque on it and spinning it up. And then when we want to stop the wheel, we, kind of did a little friction with our fingertips to slow it down. All right? That's a counter torque to spin it downwards. All right? Now, this is going to help us understand the transfer of momentum demonstration. Question?
When you say that the thumb is pointing in the direction of the velocity,
Yeah.
is it like, for example, the picture it says that it's going straight up, you mean like angle?
No, it's straight up. So if you're, it's tricky. You got to get used to thinking in 3 dimensions. Anyways, in this case, the wheel was spinning like this. All right. So the bicycle wheel, the axle was like this, straight up and down. Okay, so the angular velocity arrow is either going to be straight up and down, or it's going to be straight up or straight down. Same with the lab stool. It was spinning, and if you look at the base of it, there's an axle that's standing straight up. So angular velocity is going to be either straight up or straight down, depending on which way you spin it. And I was always going like this, so straight up. All right. Now, I'm going to give you another example with the Orlando Eye. Right. So the Orlando Eye, raise your hand if you've ever been there to the Orlando Eye. I'm going to have to try it one of these days. Okay. Now, this is a picture that I like of the Orlando Eye. And I spent about an hour this morning looking at videos and stuff to figure out Does it spin from this view? Does it spin clockwise or counterclockwise? And it turns out that it spins clockwise. So make a note, Orlando Eye. If you look at it from the west side and you're looking east, it spins clockwise in this sense. So go ahead and make a sketch, over an Orlando Eye, and it's, All right, now, what was your name again? Lexi? Okay, now Lexi, look at the arrow. All right? So now your thumb is, right, it's pointing in. So the angular velocity from this perspective now, right? And if you look at this picture, it looks like it's a drone or maybe a helicopter right about level with the hub of the right about level with the hub of the Orlando Eye. So the angular velocity vector is going to go, so here's look at my hand, look at my hand, look at my hand, okay? So my hand is going, my right hand is going like this, same sense as the Orlando. So my thumb points into the screen, or in your sketch, it points into the paper, okay? And the symbol that we use for that is a circle with an X in the middle of it. And that's this symbol right down here. It's actually this one right here. It's at the bottom of the second yellow pane. It's actually a mathematical symbol. Now here I put a circle with an X in the middle of it right up here so that you can see it. All right? And that's actually, if you were making a sketch, that's where you would draw the arrow. Now because the arrow is going straight into the display screen or straight into your paper, you can't really make an arrow. But this symbol is to symbolize an arrow, the feathers of an arrow that's moving away from you. Okay, so you're looking at the back end of an arrow, right, with the feathers. Right? The other symbol for an arrow that's coming out of the paper toward you is a circle with a dot to represent the tip of the arrow coming straight towards you. Right? But this one, it's into the paper, okay, into the screen. Now, continue your notes, because now and you're going to make some decisions with clicker questions based on this. We're going to go behind the other side of the Orlando Eye, and I didn't get any pictures of it from the east side looking west, but I did get this guy. He's kind of down on the sidewalk. Now, the Orlando Eye from this perspective is going like this. And this is kind of, we're not looking at it straight on. We're kind of off to the side, so it's kind of a perspective view. But basically, your omega arrow is going to be going off in that direction. All right, except the only thing is you'd sketch it in up by the hub. Right? And so depending on what side you're looking at, the Orlando Eye, you're going to say, well, it's got an arrow coming towards me or an arrow going away from me for the angular velocity and the angular momentum. Right? So we have to be able to handle that. Now, I want you to definitely sketch this one. Right? So here's a perspective view of the Orlando Eye. And notice, here's a couple of the gondolas down here. And that's pretty close to the actual spacing. But I just drew 2 instead of 30 of them. Okay? And notice that the right side of it is supposed to be closer to you, so I made it a little bit bigger. And the left side over here is away from you, a little further away, so I made it a little bit thinner. Okay? So give you a little bit of perspective of this. All right, now in this perspective view, now this is the same perspective as, well, it's close to the same perspective as the guy on the sidewalk, except now we're a little bit, we're about 200 feet above the sidewalk. Okay, and we're looking at the Orlando Eye. But it's still moving this way. Okay, so if you take your fingertips and kind of, you can tell that the arrow is going to be going about like that. All right, and that's consistent with this right-hand rule sketch. And you can see all kinds of right-hand rules on the internet. But this sketch here in the lower right is one of the better ones, I think. Right? And so the sketch jives with the right-hand rule. Okay? And so, and students, it's tricky. I'll just tell you that right now. I'm going to be asking you one or two questions on the exam about right-hand rule to see if you can handle thinking in 3 dimensions. And I'll just tell you right now, it's not easy, but we're going to try it. We're going to work on it, okay? And you're going to do good on it. So let's try it right now. Let's use the iClicker for that. Kane, question.
You just did the last slide about the circle the dot. You can circle the dot since the arrow's pointing towards you.
Yeah, except in this view, we can actually draw it.
Yes, it's pointing away.
So if I was directly in front, it would be a circle with a dot.
Yeah.
In fact, if I was east of the Orlando Eye, looking west, it'd be a circle with a dot in it.
Close from left.
Yeah, yeah. All right, so let's do right-hand rule. Now, this is a different spinning system. But I want you to think 3-dimensionally and use the right-hand rule. And let's see how you guys do. Okay. In this perspective view, the merry-go-round spins as shown. Okay. Right down here, this yellow arrow. Right? What direction is its angular momentum vector? Just now, when you're trying to figure this out, use your right hand. Don't use your left hand. And I know a lot of you guys are writing with your pencil with your right hand. You got to think with your right hand when you're doing these babies. And if I see somebody on the test, the only time I ever help a student substantively on a test is if I see them on a test where I know I've got right-hand rule and I see somebody using their left hand. I'll say, come on, no, right-hand rule, not left-hand rule. And you know why I do that? Because I've done it myself. I've caught myself using my left hand. So, to think about it. So, all right, go ahead and 15 seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, and most of you got that 55% upward. And the way that you want to think about it is, here I am. I'm actually bringing my whole arm across. Okay, so my thumb is going upward. All right, next question. Also multiple choice, but definitely I want you to think carefully about it, and we'll talk about this one afterwards. Here we go. If a student, like David, starts with 0 angular momentum, takes a wheel with positive 20 kilogram meters squared per second of angular momentum, and then he flips the wheel so that now it's the opposite direction. The student must then acquire how much angular momentum? So think carefully. And I've got the 2 spin states of the wheel. I don't have the student, I have the wheel. So you have to think about the student now. This is spectacular. Okay, 15 seconds. Music. Yeah. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, go ahead. This is spectacular. It's a spectacular failure because, go ahead back to, the answer is C, which is the least frequently chosen answer. All right, now, so what this means is we've got a little bit of talking to do. All right, let's talk it over. Right now, here are your two sketches. All right, go ahead and make sure you have those for sketches. Whoa, I just inadvertently did Siri. What? Get out of town. All right. Ooh. I just typed that in on Siri. Told Siri to get out of town. All right. All right, so what we're looking at is the exchange angular momentum for the wheel. Now, whatever the wheel acquires, the student acquires the opposite. All right? So let's figure out what the wheel acquires. And all we have to do is final minus initial. So L subscript F W is the final angular momentum state of the wheel. Now we know what that is. That's minus 20. And L subscript IW is the initial angular momentum state of the wheel. And we know what that was. 20 positive. So here's my numbers. Plug in time. Minus 20 minus a positive 20. Come here.
At the bottom, you say the wheel.
That's the answer. That's answer. That's option C.
No, option C was positive.
Oh, that's right. This is what the wheel does. And the answer is that the wheel, and you can see why it's negative 40. Okay, so the wheel changes its angle, or I should say, David changed the angular momentum state of the wheel by negative 40 kilogram meter squared per second of angular momentum. And therefore, he acquires from the wheel positive 40 kilogram meter squared per second. And that's his answer. Right? So this is what the wheel, you have the information for the wheel, and just the opposite of that is what David, the student, acquires. So let me pause for questions about this. Yeah. Yeah, wheel acquires negative 40, and the student acquires positive 40. Mm-hmm. It's Newton's third law, basically, but applied to a spinning system. All right? And so the bottom line for this, the wisdom that I want you to draw is that the student wheel demonstration, where we exchange angular momentum, that is similar to skateboarders pushing off from each other, where they exchange plus or minus delta P, plus or minus regular momentum. P equals mv momentum. Skateboarders, when they push off, that's what they exchange. And on the bicycle wheel demonstration with the student, it's angular momentum that's exchanged. And David, it was tough to move that thing, wasn't it? It's very tough to take that wheel. Once you get it spinning, it wants to stay there. You know what that is? That's gyroscopic stability. That's why gyroscopes work as stabilizers. To get it over like this, the opposite direction, is very tricky. It's very tough. So I don't know if Sir Isaac Newton and Galileo ever experimented with wheels like this, but if they had, they would have really been happy about it. So I'm giving them a big heart for the day. Kane.
So when you spin the wheel clockwise, right, you put it upside down, it's still spinning clockwise.
When I spin the wheel from left to right, as I did, Angular momentum is up. When we flip it, its angular momentum is down because it's still, but now it's spinning this way, from right to left, if you look at it. So I'll post these YouTubes and you'll be able to view them and stuff like that. It'll be good. All right, now, last comment I have in chapter 5 concerns this diagram from page 88. And I'm just showing it to you. This is called a phase portrait for an oscillating system. And we'll talk more about this probably after exam 2. And it is a diagram that shows the motion of an object in another abstract space. Now, last time we did that, we had a velocity graph where v was on the vertical axis and time t was on the horizontal axis. The area of it was distance traveled. In this kind of diagram, this is called phase space, where momentum component is on the vertical scale and the coordinate that goes with it is on the horizontal scale. In that kind of a graph, the area enclosed by the motion is measured in angular momentum. Kilogram meters per second times meters is kilogram meters squared per second. That's angular momentum. And my wonderful student, the reason that, as you'll read at the end of chapter 4, end of chapter 5, if you haven't already, is that this diagram, phase space diagrams and phase portraits, are probably the easiest way to understand the quantum world of electrons and photons, where energy levels of electrons are only permitted at certain energy levels and no others, unlike the energy levels of a basketball, which can assume any energy level from 30 meters on up and all the way down to 0 meters. With electrons orbiting an atom, it's not the same. And we'll get to that probably after exam 2, but for right now, what I want to hit with you is the idea of heat. This is a cool picture. It was actually on the NASA website, Astronomy Picture of the Day, on Sunday. It's an image of a supercell thunderstorm out in eastern Montana, and that's where I used to live. And boy, there's some great storms, but I actually saw a storm a little bit like this, not quite as cool looking. This looks like an alien spaceship or something like that. But I've seen storms cool like this last time I drove through the Everglades from Fort Lauderdale up to Orlando by way of the Everglades. It was kind of cool. And that thunderstorm is a gigantic heat engine. And so we're going to talk about heat energy. And these are the 3 basic topics in chapter 6. The kinetic theory of matter. In other words, when you add kinetic energy to a beaker of water, you can measure the amount of kinetic energy you have. It corresponds to a certain rise in temperature. So the idea is that matter itself, the molecules and atoms that you cannot see, they each have kinetic energy. And the theory is that the average kinetic energy is proportional to the temperature. Right? And that's going to be important for us. Another idea is thermal equilibrium, because it leads to the idea of heat transport. So that thunderstorm had buku heat transport phenomena rolling. Number 1, convection. Here's another convection system that's really even bigger than that. A hurricane. Huge. And hurricanes only rise in the late summer when the waters off the coast of West Africa have heated up, and in the Caribbean and the Western Atlantic have heated up enough to store a lot of energy. And so heat transport from chapter 6, section 10, and so on, We're going to be talking about that. And then we're going to also talk about how to heat things up and cool things off, because different elements, excuse me, different elements heat up differently, and different molecules. So a rock will heat up differently than water. And water will heat up differently depending on what phase of matter it's in. Solid water heats, in other words, ice, heats up differently than liquid water. And liquid water heats up differently than gaseous water, water vapor. Right there. And it's significant. The differences are significant. And then you see them in that thunderstorm. All right, so those are the three main concepts that we're going to be attacking in our chapter 6 on heat: kinetic theory of matter, heat transport, and the phases of matter. But before we do that, we need a basic tool, and that's called the Kelvin temperature scale. It's invented by, or named after, a guy named William Thomson, who was made a Lord of England, and he took the name Lord Kelvin back in the 1800s. And the Kelvin temperature scale, named after him, is based on Celsius. But unlike Celsius, it's not oriented to the freezing point of water. You know, Celsius 0 is the freezing point of water, and then 100 is the boiling point of water. Okay, that's nice. Fahrenheit, it's 32 and 212, 180 degrees difference. But for Celsius, it's 100 degrees difference. Now, the baseline temperature for the Kelvin system is, in a colloquial sense or an informal sense, the point at which, or the temperature at which, all molecular motion ceases. You know, I just got finished saying that the kinetic energy, the 1/2 mv squared of all the molecules of air in this room, or the molecules of nitrogen and oxygen, a little bit of CO2, in this room, you could figure out how to add them up, and the average is proportional to the temperature. Okay, but at some point, that molecular motion, in the 1800s anyways, they thought that molecular motion would cease. Now we now know that it doesn't really cease because of quantum theory. But another good way to express this, the 0 point, and this is better, is that it's the temperature point at which no work can be extracted from the system. So if you think about a heat engine, it's got to heat, and it's got to expand and move a piston. You know, like in your car, if you have a combustion engine, internal combustion, you detonate a small amount of vaporized gasoline with the spark plug, and it's just a little tiny explosion, and it moves the piston. The piston moves the drivetrain. You know, it's all connected mechanically. And the drivetrain moves your wheels, and then you motate down the road. All right? So you're extracting energy from the heatness of that explosion, that little detonation of gasoline vapor. And actually, if you have 6 cylinders in your car, you're getting 6 explosions all timed very carefully to keep the wheels running real nice and smooth. All right? Now, at some point, there's a certain temperature where you can no longer do that. And that's called the absolute 0 point of the Celsius scale. Now, here's the 3 common temperature scales. I use Kelvin all the time. The Weather Channel will talk about these 2 guys over here on the center and on the left, or excuse me, center and on the right, Fahrenheit and Celsius. Now, I do not want to talk about Fahrenheit in this class. I mean, I know everybody knows it, but scientifically speaking, we don't use Fahrenheit. I don't even like using Celsius. And matter of fact, I don't like converting from Fahrenheit to Celsius. Right? Now, you may remember converting a Celsius temperature to Fahrenheit when you're like in 7th grade or something like that. I hated that. And it's not, we're not going to do any of that. Okay? But we're going to do a simple conversion from Celsius to Kelvin. and because it is fairly simple. You just have to add or subtract 273. Because the Kelvin temperature scale, the degrees of Kelvin scale, are the same size as Celsius. They just have different 0 points. Okay, so 0 Kelvin is negative 273 Celsius, negative 273.15, according to this diagram. And 273 Kelvin is therefore 0 Celsius. Okay, so the freezing point of water is 273 Kelvin. Right now, most of the time scientists are going to be working in kelvins. Like in astrophysics, we don't even think about water that much in astrophysics. We think about hydrogen and stuff, but we're thinking in kelvins and not Celsius degrees. 373 Kelvin, by the same token, that's the boiling point of water. So there's still 100 metric system degrees between freezing and boiling. But now your 0 point for Kelvin is all the way down here at absolute 0. Whereas if you were going Celsius only, you'd give it a negative number. Now, I'm going to give you some questions here concerning the Celsius and the Fahrenheit system, and we're going to keep it simple. Make sure you have these last three: 0 Kelvin, negative 273 Celsius, 273 Kelvin, 0 Celsius, and then 373 Kelvin, 100 degrees Celsius. All right, so let's try a simple workout. And room temperature. So room temperature Celsius, so like over in the chemistry department, they might say, okay, room temperature 20 degrees Celsius. All right, what is that in the Kelvin scale? Go ahead and vote. This is particularly easy, but read carefully. Make sure you get it. $20 seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. Yeah, good. 293. And go ahead and make a side note. Sometimes you hear a little bit better of a round number, 300. That'd be room temperature for a fairly warm room. So some people say 293, some people say 300. But yeah, that's the conversion. Now we're not going to do a whole lot of Kelvin to Celsius, Celsius to Kelvin. Just maybe on exam 2, we're just going to have maybe one question. Don't worry about it too much. But now this one I want you to think about carefully, because this is related to the kinetic theory. So this is what, question 4? Mm-hmm. What's the advantage to the Kelvin scale? $20 seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. Yeah, most of you voted for this one. Now, side note to this, hopefully you're using this as the basis for notes. The reason we like this is because according to the kinetic theory, the average kinetic energy is proportional to the Kelvin temperature. In other words, you multiply the average kinetic energy by a number and you get the Kelvin temperature. Okay, there's a constant for that. Okay, now average kinetic energy is always going to be positive, so you don't really want to be on a temperature scale where you have negatives. So it jives nicely with the kinetic theory, where we think about all the thermodynamic properties like temperature, volume, pressure as being expressions of F equals ma and 1/2 mv squared for zillions and zillions of little teeny molecules that we cannot see. But we can use positive techniques of calculus and stats and trig. Okay, so this is, as I say, a useful property because of the kinetic theory. Now, let me pause for questions about Celsius and Kelvin.
So we can get the kinetic energy from temperature of things?
The question was, can we get the kinetic energy from knowing the temperature of things? And the answer to that is yes, you can get the average kinetic energy. And that's good because most molecules in a gas are going to be at the average kinetic energy or very close to it. So, so if you say, I want to know the typical kinetic energy or the typical speed of a molecule, just get the temperature and I'll show you the formula for that. Probably Thursday. All right? So yeah, you're right. Your idea is correct. All right, let's go into some more about heat phenomena. This is a cool picture of a red supergiant in the constellation Orion called Betelgeuse. And this is actually a picture of the surface. Most stars are so far away and so small, we can't really resolve any of the features of the surface. But this is actually, those bright spots are really hot parts of the surface of Betelgeuse. And it looks a little bit better in the computer. It'll look better in YouTube. But this is an infrared image of Betelgeuse. It's a red star. And one of the cool features of it, this shows the phenomenon called convection. And also the idea of radiative heat transport. Because all the energy, everything that we see from Betelgeuse comes to us through radiation, electromagnetic radiation. By the way, if you don't know the constellation Orion, it's Orion the Hunter, and he has a very conspicuous belt of 3 stars, and Orion is up in the sky fairly close to straight overhead, 9, 10 o'clock this time of year at night. So you should be able, every night when I get home, 7 or 8 o'clock at night, and I look up, and it's clear out, you can see Orion. And it's a good constellation to know in the summer, in the winter. And if you've ever heard of Taurus, if you've ever heard of Sirius, Taurus is a constellation, Sirius is a star, the brightest star in the sky. Gemini, the constellation. The Pleiades, they're a group of stars, a cluster of stars in the constellation Taurus. They're all nearby Mr. Orion, the mythical hunter. Now, this is a cluster of stars known as M13. And I'm sorry, but you can't really see it from the computer display. The colors are a little washed out. But on YouTube, you'll be able to see there's a lot of blue stars in this cluster. And blue stars are hotter. And I'll be telling you about why that is the case. Here's a really hot surface, fairly close to us. This is an ultraviolet false color image of our sun. Now this is the latest image as of about 7 o'clock this morning. They snapped this at about 8 o'clock last night, Eastern time, from the SOHO spacecraft. And if you type into Google 2 words, Soho and solar, or Soho and spacecraft, you'll get to this website, and you can look up all the images of the sun. They just snap them in all different wavelengths. This one's at a wavelength of 17.1 nanometers, and that means that this corresponds to a part of the atmosphere above the surface of the sun that's at about 1 million Kelvin, so it's really hot. We don't know why the atmosphere of the sun is so hot. The surface of the sun is about 5,800 Kelvin, but the atmosphere is in the millions. And this is the layer of the atmosphere that's at about 1 million Kelvin. Anybody recognize this location? I'll give you a hint. It's in the Caribbean. Anybody? Bueller? Nobody? It's in the British Virgin Islands, Virgin Gorda. This is the baths. One of the absolute best places. It's one of my favorite places. Absolutely great place to swim. Man, oh man. It looks nice from this photo, but if you're actually there, oh my goodness. All those rocks are a form of granite. They're igneous rocks. Why are they at the surface of the earth? Because all the igneous rocks that we have come to the surface by means of volcanoes, and volcanoes form by way of convection. Here's another huge convection system, the Yellowstone hotspot. This is from a journal article a few years ago where they figured out the exact hot area underneath Yellowstone. Now, every red dot on this picture is a little tiny earthquake. Yellowstone is always shaking. It's not big shakes, but there's a lot of them. Okay? And just a little north of this photograph, or this image, is where I went to grad school in Bozeman at Montana State. And a little bit to the above this photograph and a little further to the left is the city of Missoula. And I studied there for a couple semesters. And they have a seismological observatory there. And I actually looked at some of the data that they had. Just tons of earthquakes all the time, little ones. And what they do is they map them out. And it's like listening to sonar under the sea. If you have good sonar, you can actually resolve the shape of another submarine if you're close enough. And you can tell where it is and how fast it's going. Same thing under the earth. They analyze with big computers and they figure out, okay, all this orangey part here, that's actually magma, which when it gets to the surface is called molten lava. Okay, see this big blob of it underneath Yellowstone. Right here, this is Yellowstone Park up here. See what it says here? Yellowstone caldera. That's the fancy science term for an exploded crater of a volcano that blew. And Yellowstone is actually the bottom part of a volcano that used to be ginormous, but had such a huge, catastrophic explosion, it blew most of itself out into smithereens. And it killed off, a lot of people, but I don't think there were many people then, and all kinds of animal life all over North America perished because of that explosion. Here's another view, cross-section of the earth. This reddish streak here, and then here's a different angle on it. That's called the Yellowstone mantle plume. My wonderful students, make a note of this. Yellowstone mantle plume. It is a plume of hot magma convecting. Heat transport. It is transporting hot stuff from these deeper layers of the earth down near the core. All as far down as they can see this plume. And so they think it looks about like this. And here's the core of the earth down here. It's like a little wedge-shaped cross-section of the earth. All the way out here, About 120 degrees. That's where Seattle is in terms of longitude. And then over here, 90 degrees or so, that's about where the Mississippi River is. So this is underneath North America. Here's Yellowstone over here, where this red streak boils up to the surface. And they figure, yeah, it's actually curving a little bit. They can see the shape of it. And you can see it on the previous two slides. Anyways, I think it originates all the way down by the surface of the core mantle boundary. And it's a convection system, heat transport. It's very cool. Now, we're going to talk a little bit about heat transport on Thursday, but before we do that, I want to get down to the nitty-gritty of heating and cooling. Question? The mantle plume is basically a path through the mantle of the Earth where extra hot magma is transporting. It's like bubbles boiling to the surface. You know, if you're boiling something on the stove, the bubbles come upwards to the surface. Same thing. Except the surface here is Yellowstone National Park and a huge volcanic system. And all those geysers and stuff out there and lakes and stuff, it's the leftovers of a huge volcano. All right, let's get down to the nitty-gritty of cooling. And we'll spend about 10 minutes on this and then dismiss. The specific heat of a substance is the numeric rating of how easy or hard it is to raise the temperature of it, to heat it up. Okay, so now for liquid water, there's a unit of energy called the calorie. And the calorie is the amount of energy it takes to raise 1 gram of liquid water by 1 Kelvin. So if you're at, like 281 Kelvin and you have a gram of water and you want to raise it to 282 kelvins, you need 1 calorie. All right? So that 1 calorie could come, like, for instance, from sunlight or any other heat transport method. Any other way, like a match, if it's just a small amount of water. 1 calorie is equal to 4.184 joules. All right, so if you're thinking kinetic energy, GPE, gravitational potential energy, joules, Newton meters. Yeah, 1 calorie is equal to 4.184 joules, 4.184 Newton meters, 4.184 kilogram meters squared per second squared. A calorie is a good bundle, and we usually use it for thermal processes because it's oriented to the thermal behavior of liquid water. And for that reason, we use the symbol C for the specific heat, and we say that C is equal to 1.00 calories per gram of liquid water per Kelvin that you change the temperature. So, and C is the specific heat, and for some reason Siri keeps listening to my lecture. Specific heat is the quantity, it's the property of a material that encodes how easy it is to heat up. And it doesn't matter, it's not just H2O, it's also the state of H2O. So for instance, for solid water, the specific heat is different. Solid water, in other words, water ice, from the ice cube bin in your refrigerator. Yeah, if it's at 0 degrees Celsius, 273 Kelvin, it takes half a calorie per gram per Kelvin to raise the temperature. Right? So we say that C is equal to 0.50 calories per gram Kelvin for solid water, for ice. Right? And that means that ice is easier to heat up. You know, if you want to change a gram of ice by 1 Kelvin, all you need is half a calorie. But for liquid water, to raise 1 gram of liquid water by a Kelvin, you need a full calorie, twice as much. All right. Now, question.
You said 1 calorie equals 4.184 joules,
Yep, 1 calorie is equal to 4.184 joules.
and that one would in
4.184 Newton meters, 4.184 kilogram meters squared per second squared. Now, let's talk about the difference between the liquid and the solid phase. The difference is in the solid phase, you have for water anyways, you have a crystalline structure. You have like the 6-sided shape of a snowflake. Okay, those crystalline bonds, they're pretty tough. All right? And below 273, those bonds will form, and they represent a lot of energy. Right? And for water, it's 80 calories of energy stored for every gram of liquid that you freeze into solid water ice. So if you have a gram of liquid water at 273, your cooler has to extract another 80 calories to turn it into ice at 273. And then you can start cooling it down. Now, these are some of the specs for water. Everything else we're going to look up on tables. So don't worry about memorizing all this stuff. If you need it for homework, it'll be in your homework. If you need it for a test, it'll be on the cover page. But just make sure that you note that the intermolecular bonds, we also have to deal with that. So when we're heating ice, we're changing the average kinetic energy of the ice molecules. If we're heating liquid water, we're changing the average kinetic energy. But when we're melting, we're breaking the bonds between the intermolecular, or between the molecules. Now, here's a recent cover page, or a table that was on a recent exam, the cover page. Right, so, on this test, I asked some students some questions about silver, gold, and aluminum, and H2O. Boiling point. Now, here's specific heat. This third column is the latent heat. Let's take a look at this one. For water ice, the latent heat, this is the amount of energy that it takes to break apart, smashing and crashing, all those intermolecular bonds that make it ice. You don't have that when it's a liquid. So you got to break those bonds apart. And if you have a gram of water ice, it takes 80 calories to bust them all up. All right? 80 calories per gram. That's known as the latent heat. The latent heat of fusion, L subscript F. Now we're going to use that in the next calculation. Here we go. And what we're going to do is make a cup of tea for a polar bear up north. And polar bears up north, they have a lot of cold ice up there. So let's say that we have 400 grams of water ice at 268 Kelvin. All right, so that's below the freezing point, below the melting point. And we want to turn it into liquid water all the way up at the boiling point, 373 Kelvin, because we're making tea. All right? So there's our objective, 400 grams from 268 all the way up to 373. Now, in between those two temperatures is a phase transition, the melting point, 273 Kelvin. So let's make a note of all this stuff. Now, the latent heat for melting water is 396 kilojoules per kilogram. We're not going to use that form. We're going to use this form, 80 calories per gram. Those are equivalent. Okay. And for specific heats, we already know what those are. 0.50 calories per gram Kelvin for ice, 1.00 calories per gram Kelvin for liquid water. And our strategy is the following. we're going to heat the polar bear's ice from 268 up to 273. All right. So in that heating stage, we're going to use the specific heat of ice, 0.50. We also have to melt the ice, all of it, at 273 before we can raise the temperature. All right, so we have 80 calories for every gram, and there's 400 grams. So we got a lot of energy just to melt it. And that's before we even budget an inch above 273. So once we all melt it, then we heat the liquid the rest of the way. Now that's a delta T of 100 Kelvin. The first delta T, 3A, that's a delta T of 5 Kelvin, so that's a little smaller. But, it just depends on what the problem is that you're working on. You might have a bigger or smaller delta T. All right, so those are our specs. Now I'm going to trot those specs back out here on the next page. Here we go. Here are the two equations that you'll need. The first is for heating. And it says, take the number of grams in your mass, M, and the specific heat, C, and then how many kelvins you're changing the temperature by. All right? And multiply those together, and that'll be the Q, the amount of energy, the amount of calories needed to heat up by that delta T. For melting and freezing, you just simply take the number of grams that you've got times the latent heat of fusion, 80 calories per gram. So 80 calories for every gram that you've got, and if you've got 400, multiply by 400. All right? So that's M times L subscript F. Here we go. And here are our temperatures. 268 starting temperature. And so the first heating stage is plus 5K, plus 5 kelvins. Second one is 100. And in between those, we have melting. All right? So that's 400 times 80. And let's do the first heating part. Okay, this is what I call heat melt heat. This is one of the traditional brain burners of Physical Science 1121, heat melt heat. All right, so we got 400 grams. It's ice, so we use specific heat, 0.50. And we're raising it from 268 up to 273, so that's plus 5K. All right? And that works out to 1,000 calories, because grams and kelvins cancel. The second heating stage, I'll do this. This is actually the third part of the process, but I'm going to do it here for the second step. 400 grams again, but this is liquid water, Anthony. So what we do here is we use the specific heat of liquid water, 1.00. And now we're going 273 all the way up to 373 because we're making tea. So 400 times 1 times 100, that's 40,000 calories. All right, now the last task, it's actually the second task, but it's the last calculation, is melting. When you get to 273, the temperature stops for a while everything's melting. So you're burning your propane heater, you're melting that ice, but the temperature's not changing until it's all liquid. And then so this tells you how much propane you've got to burn to melt it all. 400 grams times 80, 32,000. And so the total here is 73,000 calories. You add up all three of these. 1,000, 40,000, 32,000, total of 73. So that's the amount of protein. So that's how many calories you need in your propane tank to help out your friend the polar bear to make tea. That's the latent heat. Yeah, latent heat of fusion from the table. It's a measurement from the lab. All right. Homework 11 will activate tonight sometime. It'll be small, but you'll have some heat melt heat in there. Okay, you're dismissed. I'll see you on Thursday. No, get it off the YouTube because we got to get out of here. Can you turn the lights on?
I got 2 quick questions, if you don't mind.
What's that?
I have 2 quick questions.